basis of design is very important in any design. So especially because the basis of design will govern the theme of designing and govern the design. So most of the people, as soon as we get a building, straight away we go to we put a column, we put a slab arrangement, and put the forces and try to go for modeling and try to do it. But we need to come up with a proper basis. We have to look at the options available and try to see what is the best option that is suitable for that particular place and at that particular time, considering not only the cost, time, and buildability. So let me start my talk. As Kirivaran correctly said, my colleague, former colleague who has been working with me on many tall buildings. So as a young engineer, I was very proud of him, very hardworking person. Unfortunately, or fortunately for him, he's more his passion is to teach. So he has joined the university, but he had been working with me on many tall buildings during his stay with us. So, we were lucky. I was lucky to get involved in many tall buildings during the last 10, 20 years. So these are the buildings that we have already done. Some are proposed. Some are most of the buildings we have completed. So, and also why we need to learn about it is now. This is what you see, the emerging skyline in Colombo. It happened during the last 5 years, 5 to 10 years. So we were amazed to see the change in skyline of Colombo. You can see the number of buildings that has come during the last 5, 10 years. And also we have a lot of projects that is going to come in this port city, new 4 square kilometer. So basically, if we learn the art of design, then we can retain our engineers as well as retain the knowledge within the country, as well as we can also retain the financial. We can also get the financial benefits because of this development. Otherwise, there will be a lot of foreign consultants coming in and setting up their firms, and most of the money will go outside, and the knowledge also will go outside. So unless we train our young engineers and make them ready to take up these challenges, we will not reap the benefit of these developments. So with respect to the basis of design, as a structural engineer, we have to look at mainly not only the gravity loads, especially when it comes to multi-stories and high-rises. We have to look at gravity loads, that is the self-weight of the building. With height, it becomes larger and larger. And with respect to the lateral loads, we have to look at the wind load. I know Jaffna, east and northeast has the highest wind loads in the range of 50 meters per second. So very high wind speeds you find in those areas because the cyclone path is along that area. So we have to wind load. If you are designing any building there, it will be very critical. Wind load will be very critical. Especially even a small building. I see now, if you look at the roofs, because roofs are critical with respect to the most of the roofs. Now I have seen in Jaffna is hip roofs. That is very good because you have a higher angle, and because of that, it keeps the roof down. Earthquake is also a very important aspects, and now people after the tsunami talking about it. When we study, there is in this Mana Basin, there is a soft zone, so there is a possibility of hotspots. I will be discussing all that during this talk. So when you look at a multi-story building, so we have to, we normally do, we have to analyze the building. So we have a couple of analysis, the model analysis, then the gravity load analysis, lateral load analysis. We have wind load, static, as well as dynamic analysis, where we calculate the accelerations. And with respect to earthquake, we can have linear analysis for normal structures like static, and also we can have dynamic analysis using a response spectrum. So we will discuss all that in this talk. So, and also the loads. When you have a load, we not only talk about a particular load applied on the structure. We have to look at lot of combinations. We normally consider about 200 combinations with respect to high-rise buildings. So this is the service combinations, especially one dead, one superimposed dead load, and one live. Likewise, with wind in X direction, Y direction. Also, and also we have to combine ultimate combinations. There are wind ultimate combinations, and also earthquake ultimate combinations. So actually, the factors that you see is based on the Eurocode. So you can have many combinations. Now, say for instance, with respect to wind, for a small building, we consider in X direction and Y direction, but in a tall building, we consider wind in every 15-degree direction, because we use wind tunnel test to calculate the disease. So all these combinations has to be put into the your program, and then try to analyze. So with respect to dead load, we have to look at the finishers, flow finishers. Generally, for flow finishers, mainly the screed concrete, maybe false, there may be some raised floors, so many things that can happen. So we have to correct, generate the finishing load will be around 1.5 kilonewton per meter square. And the non-structural walls, finishers. Now, say for instance, we have walls, and then it can be brickwork, it can be block work, it can be dry walls. So depending on the loads. So let's say if you have brickwork, if you're using 4.5 brickwork, your partition load will be around 2.5 kPa. If it is, if you are using part 9-inch brickwork, your partition load will be around 5 kPa per meter square. If it is a block, hollow block work, your partition weight will come down to about 2.5 kPa. If it is dry walls, your partition weight will come to about 1 kPa. So basically, in a multi-story structures, we need to reduce the weight of the non-structural elements like walls, partition walls. So very important to understand. If you calculate 1 meter by 1 meter by 1 meter brickwork, 9-inch brickwork, will weigh up nearly half a ton, right? So therefore, it's very important that we control that. And the cladding loads. Now, that is the cladding loads are the loads that is coming in the boundaries, where when you are calculating a multi-story structures, you have to calculate consider the windows. Otherwise, if you overestimate the load, you will be over designing, and the columns, beams, and the foundation. So therefore, accurate calculations of the dead loads is very important. Otherwise, because we are putting factors onto that, and we need to calculate. And the next thing is the building services. Now, when you talk about multi-story buildings, there are building services for air conditioning, lights, lot of, and also ceilings, etc. So generally, if it is a apartment building, you don't get so much of. So generally, I would recommend for office building with office building. Uh, about 0.5 kPa load, kilonewton per meter squared. For an apartment building, you can put about 0.25 kPa load. Okay. So live loads, the car parks, we normally, for the driveways, we normally use the British code BS 6969. 6399. So basically, it gives the recommendation for car parks like 2.5 for the parking areas, driveways 5, likewise. And the ceiling weights I discussed, and the crowd loading. But now what we have to understand is when we design a building, we design for a particular purpose. But actually, what we have to understand is this building is going to last more than 100 years. So, and also the purpose can change. So when we design a building which should be futuristic, that is why I'm saying you just cannot just go and do something and then actually, so it should be flexible to change. Today's apartment building can be office building tomorrow. Tomorrow's the office building can be turned to. So when you're selecting the dead weights, we have to have a logic with respect to. So we have to have a minimum load that we need to design a slab so that it can accommodate the future changes. And we have to have large column spaces so that we can change with time. Okay, so we will discuss this with time. So and also here, this is a good example. We design for a particular load, but during construction there is always additional loads for stacking purposes. So sometimes if it is more than our live load, we have to ask the contractor maybe to support the slab in between so that it will reduce the slab loads. These are the services at different levels, especially at the bottom level, all the services. So the service loads, you cannot just blindly take 0.5, but if the service loads are very high, we have to assume a higher load. And also there are sometimes the water tanks. We have to take the water load, the machine rooms, generator rooms, the kitchens, laundries, and the parking floors. So different areas you have to look at the different. So this is the typical material weights that we can use. What you have to understand is the brick weight is around 20 kilonewton per meter cube, whereas hollow block is around 14 kilonewton per meter cube. So we have to educate the client to change for the sake of economy, to change from brick to block. It's very difficult task, but we need to, and these are the recommended loads. Now you can see the finishers for officers 0.5, partitions 1 because the drywalls for the partitions, and the services 0.5, and live load is 3 based on the so basically you can use these charts to calculate the weights at different areas. And also multi-story structures, we can reduce the flow loads, flow live loads when you go up as per the code. So basically, the reason is there's always a probability in loading. You won't during the lifetime of the building, you will not get the 100% load. So generally, first floor we do not reduce. Second floor 10%, 20%, 30%, 40%. From fifth floor onwards, we can 5 to 10, 40%. After 10 we can reduce up to 50% of the live load. And with respect to very large areas, so there is a provision in the code. We can reduce about 200 square meters slabs 25% of the live load. So likewise, the code, these are the probabilities that given by the code, which we can use. So when you look at a particular slab, you will have different type of loads. Maybe the green color is for the planters. So you have to have the landscape, a particular load, right? So when you design something, you have to show all this in your drawing so that the contractor knows how you have designed and what are the assumptions that you have done during the design. Similar in a particular slab, you will have different loading at different levels, which we need to show by a chart. So these we may not be doing now. Better start practicing. And mainly, other thing is what I've always wanted to tell you all is we normally rely on the computer to get the vertical loads. So generally, I always make sure we do a manual calculation and check the computer load, because computer is garbage in, garbage out. So we might make any mistake. So basically, you do a manual calculation, maybe, and check whether this your loads are matching with the computer software. So these are good practices. This is what we wanted to introduce in this thing. Let's look at the wind loads. So when you look at wind load, we just cannot take a particular wind load and design. So we need to consider different aspects: the exposure conditions, where your building is, and also the wind climate studies. How the wind varies with time of the year, and what is the return periods in a particular zone. So we cannot just go and go and see look at the CPT chapter 5 or BS codes or other codes, and try to get a figure and try to put into the listing. So it will differ from place to place and based on the elevation. And sometimes we might need to do wind tunnel studies that is recommended based on the slenderness of the structure. etc. And wind design, we need to look at two things. One is the strength, which our building should not fall because of the wind, and also people in the building should not fail, should not move due to the wind, and also when there's a wind, especially in tall buildings, this is one of the major problems where the top stories can feel the motion. So we need to make sure that it won't happen. And also, when there's a wind, there is a deflection, and we have to control the deflection. That is a serviceability condition. And also, there is a wind-induced drift between two stories. Relative to this story, this should not go beyond 0.2%. Sorry, 2%. Right? Height over 500. And also, when you build buildings, you will find that people, the wind pattern changes, and then the people at this level will feel uncomfortable. So pedestrian wind comfort study also very important with respect to wind. This is a cyclonic wind. You can see it's very. This is the wind forces that we designed the building for, the cyclonic wind. It is in the range of 48 meters per second. During a cyclone, Jaffna, you will get much higher wind speeds. So this is the wind speeds that we designed the building for, not day-to-day buildings. Now, this is what happens after a cyclone. You can see all the gable roofs are gone. All the gable roofs, but hip roof remains, because because of the wind, when the wind blows, it sucks. If the roof angle is very low, it sucks, right? Because if the roof angle is high, it will hold the roof without flying. So Sri Lanka, these are the wind speeds that we have. This is December 2000. I can remember 1978, there was a cyclone passing northeast, and so so these are the wind speeds that we have. So what you have to understand is most of the cyclones are moving here, so your area will get affected. So wind is a critical, even you design a smaller building, the roofs should be very well designed, otherwise there will be a lot of damage. The main problem is, as structural engineers and engineers, what we have to understand is, due to natural disasters, there's a huge loss to the infrastructure, so it's very difficult for a community to gain control over the disaster. So there will be a lot of life loss, material loss, and also a lot of economical impacts to that region. So we have to, as engineers from these northeast areas, the cyclones are major issues. I always warn the people in the south, because we can see recently there was a cyclone very close to passing very close to Colombo. So I always warn them, what we are using in Colombo is very low. So with respect to these are some of the Colombo statistics. It may be vary from place to place. So somebody has to study and get all this data for the Jaffna region. Maybe Kirivaran can do that with his university students. So we have to study at least up to about 10-20 years, and then if you look at Colombo, we can see there are every day there are peaks like 20 meters per second every year. So and also the dominant wind direction is the southwest wind direction. So similarly, we have to study the wind climate data. So I think somebody from your region need to study the wind climate data affecting that region. I don't think nobody has done it. So we have installed these are anemometers to monitor the wind. So basically, we have installed a couple of anemometers in Lotus Tower, Hyatt Hotel, and to look at the wind data at different levels. So these are some. So because sometimes we think there is, it is the cyclones will not come to Colombo, but I have my doubts. So as I said earlier, the north is the highest wind zone. So most of the normal structures shall be designed for 49 meters per second. With respect to Colombo, it is a very high wind speed. Post-disaster structures like hospitals, schools, and also very important structures, even multi-story buildings, I would consider that you need to design for 54 meters per second, because we cannot build multi-story buildings or design after, if there is a damage every cyclone, then there will be huge infrastructure cost to the client. So whatever, so basically, I would recommend for you all to design all the structures for post-disaster for multi-story buildings, because you try to save a small money for the client now, but he will suffer in the long run, and the communities suffer. And also, you have to understand. We normally now cyclone wind speeds. It's the ultimate wind speed. It's we consider based on the data. It's a 50-year return period. So possibility is not every 50 years it will come, but the probability is the return period is 50 years. Now, say for instance, the tsunamis, the return period is 400 years. So after this, after this tsunami, I don't think we should not worry about tsunamis, because it won't come. So that is these disasters which are natural disasters. So there is a pattern where the stresses will build and then it will burst in a particular pattern. So similarly, weather also similar, unless for with respect to wind, my worry is due to the climate change, these wind patterns can change. So therefore, but since anyway these are very high winds. Zone 1 is designed for very high speeds. We don't have to worry. But the people who are in zone 3, who is considering very low wind speeds, need to worry, because if the climate predictions are wrong, we will get into trouble, because this infrastructure is designed for a 38 meters per second wind. And also, when you look at the service conditions, these are the service conditions. we have to look at these are mainly relevant to high-rise buildings. For 1 year, we consider a 20 meters per second, 1 year return period. If you can remember earlier, we can use, I showed you to Colombo, every year you get about 20 meters per second. So this is how we have developed. Actually, it's our group that developed. Mr. Kirabaran also contributed to these values, and Professor Mendes. So 5-year return period, we use 28 meters per second, and 10-year return period, 30 meters per second. So these values are checked for serviceability condition. That means when we design a tall building, we need to satisfy these winds. The idea is, now say ultimate limit wind comes in 50 years, not every year. Every year we get this kind of wind maximum. So when if 50-year wind, if the people on tall buildings can feel, it doesn't matter. It's only after 50 years. If every year you feel the motion, or every day you feel a motion, then there's a problem. So we check for these three, and we have different limits for acceptable limits for these ones. And the deflection, we normally look at the 20-year return period wind, and not the 50-year return period wind. Deflection and the drift. So when we are designing a building, we do not consider only one wind speed. Ultimately, mistake, yes, we design for 50-year return period wind. We multiply by factors which accounts for about 200-year return period wind. When you consider the acceleration, the service conditions, we consider low wind speeds. So these are the wind rows for this is the normal wind, and also this is the extreme wind rows. These generally we have to give these climate data to the wind tunnel people so that they will calibrate their wind speeds according to that. And when you talk about the wind, if your building is in the flat terrain, you consider terrain category, so you will get the full blow. And then when you this is the open country, and then if you are in the suburban, because there are we can see there are blocks due to this thing. So you might, the lower ones will not get much wind load. You can have a lower wind speed. Higher basically this is the urban areas. There will be a lot of buildings. So when we are designing high-rise buildings, we normally go for a wind tunnel test. We also the interaction of the other buildings also need to be looked at. So so there are a lot of software you can get a preliminary idea about the wind modeling. You can model a city, you can model a building, and also this is called FSI, that is called fluid structure interaction. So when the wind blows, the structure moves, and again then there is a buffeting action, and you can see. So it's a very complicated modeling technique. So the computer software is very advanced. We call CFD. That is called computational fluid dynamics. These techniques are used in aeroplane construction, also car manufacturing. Now it is applied to buildings. These are very interesting software. If there are young people, better get hold of this software. It's available now. This is the software that we have used is called Fluent, and also I have used SolidWorks. It is a very easy to modeling software. We can use that, and even Autodesk has introduced a software called Flow. You can use one of the softwares to get an understanding. You can see where the Lotus Tower, the building is moving in a one frequency, and also you can see the antenna is moving in a different frequency. So very complicated analysis you can do now. This is a topology model that we have used. How a building will differ the same building area, but two topologies. You can see the frequency of this is less than this. The movement, the periods are different. So the reason is the topology is different. So when the wind blows, it blows around and through. So there is this we have to understand is the topology of the building, that is the shape of the building, is also effective. So basically, what happens is when the wind blows, wind breaks. It touches and it breaks at a particular point. So we call it vortex shedding. So the unknown factor is there is a difference, like half a second difference, the shedding of this vortex and this vortex. Therefore, although the building is, the wind is moving from this side, because of this shedding frequency different, there will be a movement of the building in this. So we call it crosswind moment. We call it crosswind moment. So crosswind moment is very critical, especially when we design high-rise buildings. So and also you can see the crosswind effect is different with the shape, right? So basically, when you have voids, it will be some more different. So sometimes for complicated structures, we need to go for wind tunnel test to understand the real behavior of the structure. This is a CFD analysis that we have done, where you can see the vortex shedding and the wake. It depends on the shape of the structure. For the same wind speed with different shape, just round corners with a square, you get a different vortex shedding, and also different force in for. So the same area, so you just calculating the pressure into area will not the same thing when we come to the topology. And also when the wind moves, it speeds up. The force here and here is completely different. So we have to do a proper study with respect to CFD, or you can see you have a negative force behind, and you have a positive force here, and it varies. So you can see with the height, you, at this level, you have a different shading. You have a different shading here, different shading here. Okay. So it's very complicated. And in this one, when we actually Kiribaran did this analysis, I hope. So basically, we have this is the building. It's like a wall. There were few buildings behind. So we were worried what was going to happen because of these buildings, and these buildings can get affected. So you need to properly analyze these buildings. Now you can see this is Shanghai. You can see where this building, when you go up, the shape differs. I told you there are huge wind forces. To reduce the wind force, they have cut a hole. And if you look at this Jimmao tower, you will see this kind of detail here. This is also to reduce the wind speed here. Now, if you look at the Shanghai tower, it's a 600 tall building. Every section, it's different. And the shape has been designed based on the wind tunnels to reduce the wind forces. Because by that, you can reduce the cost. What happens is, why they have done it? Now, let's say you have a pole-like structure, the same cross section. When the wind blows, we have a shedding. The same shedding will happen provided you have the same wind velocity. So the shedding frequency will be, if this shedding frequency equals to the natural frequency of the pole or the building will resonate and fall. So this is why in tall buildings especially, they will not have the same shape throughout. So basically what they do is, when we design something, we try to confuse the wind. So therefore, the shedding frequency will never match the building frequency, and therefore it will not resonate. So this is the Twin Peak residencies. Mr. Kiribaran was my design engineer, where already the structure is completed, and this one we have used a wind tunnel test. This was done in Sydney, and this is the building. This is I think this is the Altia Tower, and here we also design a new tower. This is called Shangri-La Towers coming there. This was also put in the wind tunnel, and so generally we model about 500 meters radius in the wind tunnel, and this is I hope I have some slides. So from here we can get the building forces, we can get the cladding forces, and also we can get the pedestrian level forces. This is the wind tunnel that we have used for the Lotus Tower. I have been to all these wind tunnels. So this is the tower, and it's a very long tower. This we did in China, and we got all the forces based on the wind tunnel. So this is Prime Grand Residences, one of other projects. This was done in Colombo 7. All the buildings in Colombo 7 cannot go more than four stories, but we got the permission to go up to 35 stories. So this was also model in a winter. These are the pressure taps to these are all pressure taps where they can sense the pressure, and this is used to get the pressures on the facades. You can see this is a CFD analysis where you can see the high pressures in the thing, and then here you get low pressure. So we can very difficult to calculate using codes. This is a comparison where this is the CFD line, and this is the code prediction, and this is the pressure taps, the wind tunnel test. So if we use code, is it conservative? If it is CFD, in this case, very conservative. And in this case, again, you can see this is the code prediction. This is not conservative code predictions, and here you can see the actual wind tunnel test. So a lot of guesswork in this whole thing, but we always consider the wind tunnel test is the ultimate solution for these ones until this CFD matters. Here you can see from the CFD, different areas, we can get the pressures. Now, most of the time, to do a wind tunnel, it will cost around $35,000. But a lot of people doesn't want to go to wind tunnels, or try and think that we are doing experiment with their money. So we have to use CFD methods to calculate. There are different type of. This is called a rigid body. This is called a elastic body, where this will move with time. This is, and also we have used for the petal separate. So even we can. There are different type of internal testing. I'm not going to confuse you now. So even for the antenna, we could do a separate internal. So generally, the prototype is about 1 in 400 to 1 in 500. So when you do a pressure tunnel, you can get very high winds, which we will not be able to estimate using codes. If we made the code, so generally we design the facade to about 5 kilonewton per meter square, very high wind speed. So wind effects, generally a 10-story building will move about 15 millimeters. 30-story building will move around 50 millimeters. 50-story building will move around 200 millimeters. If mainly the problem is the people on tall buildings, we will have perception issues. The people with very, very low very sensitive people can even sense 5 millig vibration. But most of the people are in the range of 10 to 25 millig. So when we are designing tall buildings, especially, we make sure that we design for about we design for generally officers, we design for about 20 millig, less than 20 millig. Residential, we design for about less than 15 millig. So people, this is sometimes in a high-rise building, you might get your pools water. So if this happens every 50 years, it's okay. But if this happens every day, that's become a nuisance. So you have to be very careful when you're designing. So basically, how we resist the wind is the main thing. How we are going, what is our basis to resist the wind? We can use our rigid frame to resist the wind. So we should make sure the allowable deflections are met. Our frame is enough. This so basically, with my experience, I will tell you, you can go up to about, let's say, 4 to 5 stories on this. When you go above that, we have to incorporate some shear walls, right? Some shear walls into the. So in this, let's say you have a frame like that. Maybe you can use a core to resist the shear wall, or you can use frames coupled with the core. So, so if this is only rigid frame, that is, it's an unbraced frame, where wind will be taken by that. And sometimes if our cores are very large, the total wind load can be taken by the core. Otherwise, we can engage the frame and the shear wall. Those days we used to analyze this because there were no software to analyze 3D. So, and also you can see here, if you have 2 shear walls, if you connect this with a thicker header beam, this will act together. So these are called coupled shear walls. If your header beam is very thin, this will act separately. This will act separately. So these are called shear walls. So it will, based on the stiffness, it will take. So basically, let's say you have a building, you have a shear wall here. Let's say you have a small shear wall here. When you apply a wind force here, this wall, based on the stiffness, it will attract a larger force than this wall. It will be always based on the stiffness, right? And based on that, you can design. These are actually applicable to tall buildings, where generally we try to use outriggers and spandrel beams to connect to the core wall, so that it will act together. So for So there are many tricks that we use when we are designing tall buildings in order to tackle the wind. I will just introduce this at this course. You can see these are the outrigger spandrel beams and the outrigger levels. Mainly, uh, we put at the service levels, because when you design a tall building, you have to have a service floors every 20 floors. So generally, you can put outriggers at these levels. When if we try to do a high-rise course, we can do it. So these are my experiments with respect to the structures. So if you do not have, it's a 50-story structure. If you have a if you don't have outriggers, it will deflect 200, and then if we have one outrigger, 185, and also here 175. With this experiment, what I want like to this thing is, now this area it will act like a cantilever, and then it will due to the stiffness of the core will be much more here. Again, you can see it will go like that and it will come back. So basically, you can increase the stiffness of the core will be much frame will be much more in the upper levels, right? So here, due to the core, it will act like a cantilever, and then the stiffness of the wall the frame will take over. So always your deflection curve will be like that. These are for very high buildings, more than 600 stories. These are called super tall buildings, where you will the whole tall building is like a suspended cantilever. So so this whole thing will be a cantilever. What will happen is there will be columns at like 3-meter centers, and it is like as a one frame tube joined by a spandrel beam act together. So generally you get a shear lag at the corners, and you get a higher shear forces at the corners due to the shear lag. Again, this is for high-rise structures, where you try to have, if you want to increase these column spacing, you need to use a brace frame to brace the tube, and then you get a brace tube structure. You can see all that. The mainly what the idea is, how do you make it more efficient to resist the wind? So if it is equally spaced, it is 50% efficient. If it is all the masses is at the corners, you can balance it. So this is 100% efficient, but at least you need to go to about 67% efficiency with respect to the lateral force. These are called performance criteria, where this is the ISO guidelines, where for 1 year return period, your office building has to have about like in between let's say 7 milli-G to about 13 milli-G. For 10-year return period, it is in the range of 10 milli-G to like 20 milli-G. So this is the model analysis. Actually, there are so many buildings together. So when you analyze a building, your first mode should be translation. Okay. And the second mode should be translation. Third mode, because there are so many buildings, should be a rotation, right? If you do for one building, you will easily see that. Now, mode 1, this is a 50-story building. So generally, by doing analysis, you can get a period. This period generally is, if you want to get some idea about the period, if it is very different, then you need to, the number of stories you divide by 10, you will get the approximate stories. So this is around 54 or 55 story building. 55 divided by 10 will be around 5.5. So likewise, we can get from model analysis, you can get the mode shapes, and also the first 3 modes are the most important modes. Unfortunately, because there are 3 buildings, you don't know what mode, but definitely you know the first mode, and the second mode should be translation. So from the period, we can see period 99% is translation. Here mode 2, this is building 2. Building 2, let's say building 2. Here it is a rotation. Building 2. Is a translation here. So basically, sometimes for very tall buildings, sometimes you might not get the ideal situation, but most of the normal buildings, you will get this ideal situation. And then we calculate the accelerations, and these are the allowable accelerations. We have to we can calculate the acceleration based on the, most of the time we use the code. When you calculate in the service condition, we normally use a damping of 1%. So don't think about it. These are more relevant to the, and so for completeness sake, I have put it. So basically, this is the ISO curve. This is the accepted accelerations. Actually, for this building that we have designed, it is in this range. So it is very, and what you have to also understand, we are also using different codes to check our values, because we don't know, because these are the deflections. Deflections for any buildings, L over 500 is allowable. So height over 500. So this is the height of 500. Sometimes in tall buildings, we also go for height of 400, provided it is a very slender structure. That is also possible, allowed in codes. Here, this is the building drift. Drift is generally 0.2%. That is height over 500. Now let's say you have a 3000 millimeter building. If you divide by 500, about 6 millimeters. So basically, that means the relative displacement between this flow and this bore maximum is 6 millimeters. So you need, because if it is more than that, your facade will break. Right? For tall buildings, we can go up to height over 400. because if it is 400, we have to tell the facade people that this is building drift is much higher, and then you need to look at pedestrian level wind is very important when we build buildings. Due to the wind, buildings, people, there is no hurricanes or anything like that. For the normal wind, this is what going to happen. I think Jaffna, sometimes you get very high winds. So very important. That is mainly because when the wind it has a down flash, and then sometimes the venturi effects, and also this is the effects due to the I told you in the upper level, it called calm effect, vortex effect. So these are the guidelines. You need to make sure that velocities are less than 2 meters per second for sitting, and you all know if it is more than 10 meters per second wind, we even don't operate cranes. Sometimes we ask even 5 meters per second, we ask the crane operators to stop work. So these are some of the condition that we need to look at. So some of the mitigating measures is because especially I was talking about wind is Jaffna is a very windy area, windy place where you need to have tree covers to reduce the pressures, maybe barriers, screens, and also some cover. Earthquake conditions, a lot of people think earthquake is not a major issue, where earthquake will not happen, but after tsunami people, I will tell you the current design practice and also the world practice, and also the world what we call performance-based design practice that we do in our office. So basically, if you look at seismic monitor every day, every minute, there are a lot of earthquakes happening around. We got a major issue because of the earthquakes in this Burmese plate, and then we got a tsunami due to that in 2004. So mainly the whole world has been divided into 13 plates. We are in this Indo-Australian plate. So mainly the earth, these are not dead, it's are moving all the time. Some plates moving each other, some plates moving away, right? So because of that, the stresses will get built up, and then there will be shakes. So luckily, Sri Lanka is very close to, is in the center of the plate. And Australia also thought the same way. But after the Newcastle and Sydney earthquakes, then people were thinking what happened. So there is the phenomenon called intraplate earthquake. Not this is interplate earthquake, this is intraplate earthquake. So there may be cracks inside, and then there is a possibility of slip, right? That happens even there are many fault lines in Sri Lanka also. So there is now a lot of geologists have discovered there is fault line here, and the plates are moving like that. So plates are moving away is good, and this is about 500 kilometers from the from Sri Lanka. So basically, this is work done by Professor Abeko, we are Prera University professor. These are the history very close to Colombo. You can see there had been few earthquakes, and this is the possible plate boundaries that you can see it is moving away. So these are some of the dates and the locations according to Professor Abekon's research. So there had been 1891 one earthquake in Mayangania, between 80 to 93 earthquakes with Tangala, Tinkamoli, and Mahilupallama. 1938, there had been an earthquake in West Colombo, and also 1993 in West Colombo. So this is literature translated from Portugal, 1615. There had been an earthquake that is 300 and or nearly 400 years ago. So this has been reported by Portugal priest, and there had been about 2,000 people dying dead at that time. So this is some of the records. 1938 September level, there had been a major disaster, and also according to geologists, there is a soft subduction phase where sediment is filled with this area, and then there's a possible hotspot very close to Colombo. So what they say is we call it failed mana rift zone. So these earthquakes, 1938, 1615 earthquakes, are due to these. So main CDB is Colombo, and then something happened very close to Colombo. Then there will be a big disaster to the whole country, and we were interested from beginning on this. And then 1994 there was interest by the Society of Structural Engineers, and we were detailing according to the UBC codes, and then later on Society of Structural Engineers issued a guideline. So this is Haiti, and after the earthquake the whole country failed. You can see what happens, and this is Newcastle earthquake, Christchurch. You can see what happens in 2011 in New Zealand, and you can see the damage is on the top. I will tell you the reason. This is what is going to happen. Mainly the tall buildings are safer in earthquake. I will the main point is than the smaller, shorter buildings. The reason is, you can see this building failing. The main reason is, let's say this is the time history. Is the time. So you get very large shakes at at a very small period here, and it will die down within couple of seconds. Let's say 4 seconds, right? It will die down. So very high accelerations here, and the period is very low. When I told you the building period is equal to the number of floors divided by 10. Let's say you have 1-story building. The period is only 0.1 second, right? So that is this region. So it will absorb the highest force, acceleration. So force is equal to mass into acceleration. So when you have high acceleration, you have high force, and you will get hit. With respect to tall building, let's say 50-story building, you divide by 10, the period is 5 seconds. By the building goes here and come to the natural place, it is already gone down, right? The acceleration is very low. So therefore, you will get very much less force, but your mass is high. Acceleration is very low, right? So what happens is, especially if there is a shake, if your soil is very loose, what happens is due to the earthquake, there will be huge energy, and due to that, we will have a very high pore water pressure. When you have such a high pore water pressure, this soil becomes like liquid. So if that happens, your building will anyway fail, right? So if you're liquefied, generally when we design a building, we check the liquefaction potential. So unfortunately, we don't have shear velocity test in Sri Lanka. So what we normally do is we check the SPT values. If the SPT values are greater than 15, so there is a very unlikely chance of getting into this liquefaction. So liquefaction potential is very low. So if the SPT is less and you want to build something there, then you have to compact it to achieve such. So in order to earthquake design in Sri Lanka comes into practice in 1990s, and we normally use the Australian code because we are in the same plate, and sometimes we can also use the Indian code because India also use the similar code. If you look at the Indian code, it is very similar to Australian code. Some projects are done in Indian code, American code, some are European, and so since we don't have much control over the codes, so some people design different codes. So Society of Structural Engineers introduced this detailing to mitigate seismic because I will show you some why we have done that. And Disaster Management Center also commissioned Yunisha Peradeni and Joshua Muratua to develop a demand spectrum curve, which they did in 2015. And we use these response spectrums for Colombo, and they have done for Jaffna too, I think. And so you can also use the same spectrums. Generally, we use a method called performance-based method, introduced by CTBH, Council of Tall Buildings and Urban Habitat. and that is the method we use normally in our. So these are called response spectrums. Based on the soil category and the risk factor, you can select one of the response spectrum and apply to your building, right? So basically, we are using response hazard factor of 0.08 based on the guideline of the University of Peradeniya research, which is very valid. That is very much average between the Sydney and Melbourne earthquake risk factors. This is so we used that factor before they did the design, and I used the average between the two cities to design my building, especially the Hyatt building. So this is the response spectrum. The Tamil Nadu is considered as zone 2. So they have not given us response spectrum. So zone 2 is 0.1. So in Colombo we use 0.2. Kerala zone 3. So for Jaffna also, I think we can use a response spectrum of according to the Indian geological map. I think we also can use a response spectrum of 0.1. Here you can see different responses. So these are very low. This is the PGA value that recommended by, and the research was done by one of our colleagues called Dhananjay. So this is the book that we have published by Society of Structural Engineers, which anybody can buy that. Performance-based design is the tall building guideline. I will explain to you all that with time. So what happens during an earthquake is ground is shaking, and the building start resisting. So when something is shaking, this try to shake, and buildings start resisting the shake, therefore you get an inertia force acting on the building. With respect to wind, the force is corresponding to the area. With respect to the earthquake, it corresponds to the mass, right? So there will be a shake, and then there will be an inertia force based on the mass and the acceleration. So you can see, I showed you so you can see the wind, the force is very high at the top, and this is why it failed. And as structural engineers, what to do? Now we have a force. So we have to dissipate this force through our structure. So if we dissipate, when it happens, when they are forced, then if the beams are thicker than the columns, and it will be dissipating through the column hinges. Hinges will form and it will fall. all the videos that you saw, buildings falling, is due to plastic hinges forming in columns before the beams. Now, in this case, if we try to design a hinge in the beam, maybe let's say pin supported, you detail. So all the hinges, even the column bottom, this will survive because this is no problem. Or like that. So we also can. So actually, the engineer has you have to decide as the engineer, how do you dissipate the, so basically you have to select preferred location to have the hinges when there is an earthquake. And if it is in the correct way, then it will be, so we call this as ductility detailing. Now, this is what happens during an earthquake. This hinge failed. Therefore, if we want to survive, we have to increase the shear reinforcement. By doing that, you confine the concrete. You confine the concrete, and it can last for a couple of seconds. So as I told you, this will die down very fast. After 4 seconds, it's negligible, right? So if your building can survive, these joints can survive, and also we normally don't put laps very close to the joints. So there are rules like your laps should be 2h away from the h is the height of the joint. So likewise, these are called prescriptive rules, has been introduced by the Society of Structural Engineers. These are also copied from other guidelines. So here, again, confinement. So we have increased the confinement zone, and the laps is preferred at the center. And this here, you have a wall. Because of that, this become a short column. So in that case, we have to have more reinforcement. In this one, you can see where this is open now. So this is why we tell the contractor, you need to have this kind of thing. I know it's very difficult, but if you want to improve your ductility detail, you have to do that. And especially at the connections of the piles, you get a larger moment. So you need to have larger reinforcement, confinement of reinforcement, as you can see, 100 millimeter spacing. And the minimum reinforcement for both piles is 0.8%. Generally, for normal design, we put 0.5% for both piles. But we can prove that you need a little bit more reinforcement. And mainly, when you're detailing, most of the people die because for ceilings falling down on their head or brick walls falling down on your. So we need to, if you are designing for earthquakes, we need to have anchors to your walls, to the main frame, right? So these details are introduced in our. When we compare the wind and the seismic demand, the seismic forces, the wind force, generally the structure will be designed for the full demand. With respect to seismicity, when there is a force, there will be cracks forming, and it will reduce the stiffness, and it will not absorb the full force. It will be reduced. So therefore, we will not. If we design, let's say we can design the building to be fully elastic for the total full load, but we normally assume some cracks, and it will dissipate some load. The full load will not come to the building. If we design for full load, it will be very uneconomical. So we divide this by the full load by a thing called a ductility factor. It is in the code. So we can, there are two ways of doing it. We can use the static method, or we can use the response spectrum method. Another way that we have to do is for, this is very tedious method, where you can use the called pushover analysis, where for small buildings we can do that. We push the building. So you need to have the demand curve, and also we have the response curve, and we see where the building fails. At that point, if our critical elements are failing, then we can see the risk. This is nonlinear analysis. We normally don't do for the whole building, where we try to model a particular key element. All the fibers are modeled, and then we apply a time history and see whether it's yielding or not, or whether it's going to the critical state. So for today's lecture, I will try to be little bit. I will try to make you explain the performance-based design in a simpler way. Now, if you are client asks, what is going to happen to my building? Whether it fall down due to earthquake. So this is the question that you need to ask, right? Whatever the calculations that we do is useless if we cannot answer this question. So basically, we are assessing the damage loss. If we say, okay, your building will be fully operational after or we can ask, what do you want? Whether you want a building fully operational after the earthquake. Earthquake comes, next day you are working. Or there may be small cracks, but we can prepare and immediately occupy. Or whether we can demolish and redo, but it will not fall when the owner is inside, life safety, or whether it will collapse, but it will not harm the other people, right? So if you say fully operational, then he has to pay the cost for that. We have to put a lot of reinforcement. Say, okay, no problem, a small crack, but I need an immediate occupancy. So this is a wise decision. We have to balance the cost versus the damage. So this actually we modified a little bit to suit our country, because considering that we have a low seismicity, we decided to have these objectives. That is, we consider different return periods. That is 50-year return period, 500-year return period, 2000-year return period. 50-year return period earthquakes is very small. You have like a PGA of, if I can remember, what 4G, 0.04G. 500 years is 0.08G. Here about 1.25G, let's say. So this is a rare earthquake. This is a frequent earthquake. This is rare, but possible. So wisely, what we thought was, since we are in a very low seismic region, our objective should be, if there is a 50-year earthquake, it should be fully operational. If it is a 500-year earthquake, it should be immediate occupied. And if it is a 2000, it's a very rare earthquake, then it's life safety, people will not die, but we have to break and make the building. So this is the international standard, where they have categorized essential facilities in the way that we have done. High occupancy, they have relaxed a little bit. Standard buildings, they have relaxed a little bit. The same thing, they have gone like that. So how do we know this will break or not? So basically, we will know if the drift, that is, building drift means the floor to floor drift. Okay. So if with relative to this flow, it has a huge movement, this will break. So if the drift is less than 0.2%, that is height over 500, we can jolly well say 100% sure it will be fully operational. So we only look at, we put a response spectrum, and then we see whether limits are exceeded. If it is not, we can say the client, it will be fully operational. So if it is like 0.5, less than 0.5, more than 0.2, 0.5, immediate occupancy. If it is less than 0.1, 0.5, life safety. If it is more than 2.5, definitely it will collapse. So this is called performance. So we assess the performance due to the force, and we predict the behavior. So this is actually the future of design, not only for earthquakes, wind, as well as even for element design. So in order to do that, we need to you need to assume some stiffnesses, because actually you don't have the program cracking. So we need to induce cracking or reduce the stiffness. So these are the stiffness assumptions. If it is a wind or service earthquake, we use these stiffnesses. That means generally, let's say for example, let's say a column, 0.9 for, so shear 1G. That means we consider the area is 1. Area is equal. Otherwise, 0.9 with respect to the IG. That is we modify the stiffness. So we can modify the stiffness in the program. So design-based earthquake, that is the 500-year earthquake, we modify the stiffnesses. So beams 0.35I, shear is based on the area 1I. Likewise, we normally modify this is the maximum critical earthquake. So you modify the stiffness, and that is, and then you look at the response, and based on that you can. So I will not go to all the details with respect to the analysis. So basically this is the static analysis. We call it base shear. So it is based on the, there are several codes. This is the ACI code. So the ductility factor is based on the type of building and the importance factor, right? And this is the weight. Okay. So I do not want to confuse you on all that. Now here the response spectrum, how they develop the response spectrum. These are called response spectrum. So this is the zero ground acceleration, that is at the 0 time. This is the peak ground acceleration, and this is the response spectrum. How they draw the response spectrum is, now a small building has a natural period of, let's say, this, and the maximum displacement to a particular the maximum displacement to a particular earthquake is this. So likewise, you try to get the maximum, and then you make a displacement to acceleration by doing couple of Fourier series, and you can get this FFT, and then you can get this response spectrum. Actually, most of the codes has response spectrum up to 4 seconds, because if we are having very large buildings like 60-story, 70-story buildings, even Lotus Tower, the period is in the range of 9 seconds. So also we can see when you have very large spectrums, so we are thinking about it, what to do for this range. Hopefully we can get an answer within a couple of. So these are some of the response spectrums done by Shana Lananje. This is the response spectrum that we use for Colombo. It is 0.1, considering rock as the foundation. So if it is on soil, it will increase. So nobody has done that kind of research. And when you do analysis, we need to consider about 90% of the mass has to be participated, because mass is the main thing. You can see 90% of the mass is around 50. We had to consider about 56 modes to do that. So basically, we have to apply the earthquake in two directions. If it is, we use 100% in one direction, we apply 30% in the other direction. So, and then we can get the story shears based on the response spectrum. This is the static response. You can see static response, let's say 500-year return period for the same building. When you look at the dynamic response, it's much higher because static response is based on the first mode and the dynamic response is based on 90% of the modes, 90% mass participation. So if you look at the wind load, the base shear is in the range of 5,000 kPa, sorry, kilonewtons, 5,800 kilonewtons. If you look at, this is the stored drift. Interstored drift, that is less than 0.2, that means it is safe. I just want to show the base shear of due to, right, okay, good. Look at this, tower 1, base shear 5,100, 5,800 in the x direction. Remember this one. And if you go to the wind, tower 1 is 5,800. So that means wind or earthquake, we get the same base shear. That means, especially in countries like Sri Lanka, one is wind governs the design. The second is, if we design for wind and detail for earthquake, we can mitigate the effect on earthquake. So that is also possible. If you cannot design for earthquake, still if you detail for earthquake, it will mitigate the issue. So these are some of the regulations noted by the Australian courts. So generally, irregular buildings are not advised, and irregular mass is not advised. Let's say if you have a building like that, we normally put a seismic joint here, and if you have a transfer flow, then this transfer flow will attract a lot of mass. Mass is high, forces will be very high. Therefore, these joints has to be very well designed. Otherwise, the whole building will collapse due to the earthquake, right? So also, therefore, the mass variation is also not preferred. However, since we have a lot of software now, these are designer, if they have the confidence, we can ignore these recommendations. So I have discussed about today with respect to loads, the gravity loads, and the wind load. We discussed wind load and also the earthquake loads. next time we will discuss with respect to the building, how to plan the building from basement to roof, and how to think about it with respect to the concept. So very important, as initially we need to study, know the loads, how to apply the loads. We need to see how to tackle the loads with respect to the basis of design. And then after we get all that, we can conceptualize the total thing. So I would like to thank Professor Priyan Mendes, Shilpa Tilakrasna, who has done a lot of work on earthquakes, Kiribaran. He has done a lot of work on wind, and Shana Jananja, and Tara Guruvardhana, also one of our engineers who is now doing finished a PhD in Australia. This photo is from Siripada, looking in Colombo. It's a very, very nice photograph. That is my last slide. So if you have any questions, I am happy to answer.
Thank you very much, sir, for the very interesting and informative presentation. We have very rich audience here, including very senior engineers. If you have any questions, you can ask. Either you can put in the chat box, or you can ask the questions straight away from the resource person.
Thank you for your presentation, Engineer Shiromal. I have a question that you saw the failure of the Christchurch church. So you said that the load is higher in the top, but when you consider a building, the demand of the bottom columns are higher because we have to add all the mass into acceleration, and it will be the demand. By looking at the structure, we can see that in the top also the mass is not that much high. So what's the reason actually for the failure? You said the load is higher, but I don't think that's a reason. So could you please
load is
explain?
No. What we have to understand is now in an earthquake, force when there is a horizontal load, right? So the base is also moving with that load. So actually there is no resistance. So therefore it will the horizontal there will be no, if you resist only, you will get a force. The inertia force at the top is much higher because it's trying to resist the movement.
But inertia forces depends on the mass, no? But looking at the structure, the mass is...
correct, mass. But now if the inertia force is less, let's say now if you try to like say if you are if the foundation is on the rock, and if the rock is shaking, the lower levels, you won't, it will go with the rock, so you won't get any force.
Yeah.
Because if you resist, definitely you will get a force. So mainly now say we have I did a like a piling operation very close to EPF building. When the piling operation, when we drill the rock, there's a lot of vibration. So this vibration will be felt only by the top people, not the bottom.
Okay.
So similar situation when you have an earthquake.
Okay. So I have another question that when we do the model analysis for a building, so normally we are checking our design whether it's correct or not using the model analysis. So do we have the first mode as translation, or can we have in some cases the rotational mode? Because I have
it is like this. If it is a smaller building, now say for instance you have a building like this, you cannot get translation. Okay.
Yeah.
So you will get always a rotation. Now, if this is a smaller building, let's say 2-3 story building, you don't have a problem, right? So you have no other option unless you try to have a joint here. In that case, you will get translation in these buildings. But if you are modeling together, definitely you will get a rotation first. So the risk is if there's an earthquake, this is the mode shape is the weakest axis. If it is a rotation, then you will get a additional moments. So what you have to do is you put the response spectrum and see whether there are, or you can do a push-over analysis or see whether you are getting your first inches are in the columns, or so if that is the case, you have to make sure that it doesn't happen. So that is the case. So we sometimes the building shape you cannot get a translation, but it is not good for very tall buildings. You have to, if it is tall building, translation, if there is a rotation, first you have to change the geometry.
Okay, but if we select some structural system, even though it's a tall building, sometimes we may get the rotational mode as first mode. I think I have worked with one building with AD solution, and there I got the rotational mode, and they said it is okay. Dr. Naveed said it's okay.
Yeah.
It depends on the engineer's choice. Huh?
It's like this. So Dr. Naveed is a very respected person. So if it is now some other, now say for instance, basically there are code provisions. Now when you design some building, it will be checked by another engineer. So this engineer will be looking at the code. So sometimes if it is in the code says first mode cannot be rotation, then you will get into trouble. So basically I know I did some work in Myanmar where it is very every week you get an earthquake. So very high seismic zones, low seismic zones, no problem. If you are doing anything in the this thing in the Myanmar code states, first mode shall be rotation, second mode shall be rotation. Shall be a translation.
Okay. And I have another question. You are working in a lot of buildings in Sri Lanka. So
Yes.
I can see the values of the shear force values for wind load and for earthquake load. It's almost same, no? So my question
very
is,
much same.
yeah,
Yes.
very much same. So actually, do we have to do the earthquake analysis in Sri Lanka, or can we do only the detailing part for earthquake?
It is like this. Now, when we are doing a very tall building, it's better to do all the analysis because it will be checked by many foreigners, contractors, engineers will check, and also the clients engineers will check. So better to do all the analysis, even the non-linear analysis used to do. So if it is a smaller building, we don't need to do all the analysis. We can, if even we do detailing properly, it will survive according to my understanding.
Okay, I have one last question that I don't know whether I have taken the others' time. So
No. I mean,
is
you
it
can
okay?
ask any
Yeah,
question
okay.
at least.
Yeah. So you said that the earthquake will not affect the tall building since the time period of earthquake is very low. So
Correct.
my question is, it depends on the time periods of the earthquake occurring time period or the period of that motion. That means I am asking whether it depends on the resonance of the building, or whether it is depends on the time period, because in your graph you have shown the time period of the occurring time period. So my
Correct.
question is whether it depends on the resonance or whether it depends on the time period, occurring time period.
Now, it's like this. Now, every building has a period. That is the, okay. So actually, a tall building has many periods, but the major thing that I'm talking about is the first mode, right?
Yeah.
So shorter buildings will resonate because its period will match very fast, very quickly with the period of the first few seconds.
Yeah.
So it will have a very high acceleration due to that, and it will resonate. And also, you have two questions. One is it can resonate. If it is resonate to the building period, yes, it will fail. Other thing is it will attract. If you have an acceleration, you have attract force. Due to force, you will have cracks in your building. So both can happen.
Yeah, thank you. So in actually Nepal,
Hmm.
if you look at the building in 2015 earthquake, the low-rise buildings survive. Lot of so it depends on the where the building is located, or it's normally because in Nepal, if you say it is a soft soil, because of the soft soil, the period is amplified. That's why the resonation
Yes.
can't happen. So that's a reason, no, for the
Nepal
Nepal.
building survive or
Yeah, it
destroyed?
survived. The low-rise building survived because of the amplification happened because of the soft soil of the
Yeah,
period. Yeah,
true. So so when the soft soil, you get a higher amplification.
yeah, high
The
amplification and
tall
period was longer.
buildings, this can happen. Now, say for instance, we have a tall building in Sri Lanka, but let's say there is a earthquake in Pakistan. So the it will travel to us, and it will have a larger period. It
Yeah,
can mesh the, so large periods can measure along the high rise buildings. That is also
uh,
possible.
okay. Okay, thank you for your answer.
Sir, I have one question. Do you think that the direct displacement based seismic design approach is applicable to Sri Lanka? And have you done any designs with this method?
Direct displacement, that is the push analysis.
No, seismic design. We are using the force-based design by using a pre-ground acceleration. In the
Correct.
direct displacement-based method, you use the pre-ground displacement.
Uh, I still didn't get your. So we normally pre-ground we get this response spectrum based on the pre-ground acceleration, right?
Yes, sir.
So what is your question?
There is another method or an approach called direct displacement based approach.
Yeah,
The
direct
pre-ground.
displacement base is the push over analysis. No?
Okay.
So you push the building and see where the demand is. And then at this time, we see what elements have made has the fringes formed. So if the fringes are formed in this in the columns, let's say first hinge form up to this time, we see where the hinge form. So you can see if the first hinge form in the column, and then you can see whether it's fading or not. You understand?
Got it, sir.
Right.
Thank you very much for your valuable information. So I have small doubts. So when we design the high-rise buildings,
Yes.
Especially nowadays, we have the facade structures. So
Correct.
the facade structures actually like hanging system, especially curtain wall system.
Correct.
Yeah. So when we design the high-rise building, especially for seismic loads, we are totally taking any effect from the seismic load to facade structures. We have to consider especially for curtain wall design and connection area, or we are considering fully seismic effect catered by this particular building structural elements.
Very good question. Very good question. So if your building is when you design, if you think you have your drift values, generally I will tell my experience. We design the one tower that is very tall, like 350-meter tall building. So we were not able to control the drift due to a seismic effect to height over 500. So what we then we control the drift to height over 400, and then so that means in the event of a 500 return period earthquake, these elements will be cracking if your drift allowance in the facade is not considered this drift. So what we do is we give these drift values that we considered in the design to the facade contractor, and the facade contractor allows the movements. So your fixing should be allowed for this movement. So this is how we tackle this situation.
And also, I have one more doubt. So because normally for the mast arm structures, especially in the Lotus Tower on top, we have the very big mast arm structures, steel mast arms. Yeah. So when we design that mast arm structure also, especially for the vortex shading action, we are using the equivalent stress method, and some because with the lack of information in the code, so we are using some equivalent stress methods. So this one is actually, we can assume that there's 100% is applicable and considering all the aspect of vortex shading action.
Now, if you look at the Lotus Tower mast,
yes,
we trying to draw this Lotus Tower mast. Wait a minute, I will try to draw this. The bottom section is square. Then we have a trapezoid section. Then we have a circular section at the top. So purposely it has been done like that, a square and then at different sections we won't get this vortex shading at the same time. So what we found is mainly when we are designing this kind of mast, we design the main issue is this can fail for a very low wind speed, like according to the Lotus Tower, it's like 11 to 12 meters per second. So therefore, because it can, it is called can resonate. So we make sure it will not resonate for this kind of, and mainly when we are designing this steel structure, we look at the stresses. Generally, this can fail due to fatigue. So therefore, we normally design if the stress capacities, we normally Fy/3. So let's say it's like 300 steel, then you divide by 3 is only 100. So we make sure due to the forces, the maximum forces, it won't affect. So there are lot of cycles, million cycles within one day. So therefore, we have to be very careful when we are designing a slender, tall structure. It is like 87 meters tall tower.
Okay. Thank you. Yeah, thank you.
So I have a question related to Lotus Tower. So when you consider the building, you normally consider the first mode period is n/10, no? So similar to that one, how did you validate the finite element modeling in Lotus Tower? And another question that in Lotus Tower, you have the antenna structure. So the first mode, I think mostly it will be covered by the antenna structure. So did you get that type of mode shape or different mode shape?
Actually, it's a good question. What we observe is the building mode. First mode is a circular symmetrical structure. So we got about 7.8 seconds first 2-3 modes for the tower, and the antenna we got about the other modes were in the range of 1.5 seconds. So first you can see that this is the tower is tower modes were the first modes that we observed, and then the antenna modes.
So you modeled both separately, no?
No, model together.
Model together.
Model together.
Okay. Okay.
Okay, if there is no other questions, we can take one more burning question if there's a question. And with that, I think we can wind up for the today session. If you have any other questions, we can take one more question. If any participants want to ask another question, we can take, and then I will formally hand over to the chairman of the IESL to do the formal vote of thanks.
It's not a question, but a question from the host. Do you upload this recording to those who cannot participate?
So are you happy to upload the recording or share the presentation slide?
No problem.
Okay, thank you. Then we will share the recordings with the participants. With that note, I think we can conclude the session. And I request the IESL chairman and the organizing committee members, there will be a formal vote of thanks for the today's session. Over to you, chairman.
Thank you, sir, for your valuable experience. And now our IESL Vadakkin chapter assistant secretary engineer Kajivan will give you a vote of thanks for today's session.
Good evening, all of you. It's very privilege to me to do the vote of thanks for the wonderful session, especially our engineer Shiromal Fernando. All of us know the value of that engineer in Sri Lanka. So for your valuable time to make this event and share your valuable knowledge with our members, thank you very much, sir. On behalf of IESL Vadakkin chapter, I extend our fully grateful and thanks a lot, sir, for your valuable time. And also engineer Kiribaran, who make this event to happen, and also the committee members. And the same time, and today events, around 214 members participate. All the members who allocate your time to make this event a success. Thank you very much, sir. Thank you very much, all.
Thank you very much.
Thank you very much.
Thank you, everyone. Thank you.
Thank you. We will meet again next Friday.
Next Friday, right? Thank you.
Thank you.
Have a good day.